Welcome everybody. Welcome to our Revolutionising community monitoring on the Merri Creek. And I'm going to introduce everyone with me at the moment. But first I'll introduce myself before I introduce the presenters. My name is Julia Cirillo and I'm the Water Watch and Rapid Response to Litter Coordinator at Merri Creek Management Committee. I'm also the moderator for today's webinar. As you're probably all aware, we are recording this webinar, so it will be available for those that missed the webinar, or if you'd like to watch it again. Why not? Just before we start, I'd also like to acknowledge that the Merri Creek catchment and the land I'm standing on currently is part of the traditional owners are the Wurundjeri people, the Wurrung Nation, and I'd like to pay my respects to their elders past, present and future and emerging. And welcome to all of you, whether you're on Wurundjeri country or other country around the areas. Merri Creek Management Committee is a not-for-profit environmental coordination and management agency formed way back in 1989 to achieve a shared vision for the waterway corridors of the Merri Creek catchment. So our work includes coordinating the policies, works and activities of member groups, carrying out revegetation and remnant vegetation restoration works at more than 80 sites between Kalkallo in the north right down to the Yarra, providing environmental planning advice to member councils and developers, involving the community in managing waterways and their parklands, educating the community about environmental issues, and negotiating with government on key issues. Now, when I mention MCMC members, they include all municipalities in the catchment, which are the cities of Darebin, Hume, Moreland, Whittlesea, Yarra and Mitchell, plus the Friends of Merri Creek and the Wallen Environment Group. Reps from all these groups form the Committee of Management that guides MCMC activities. MCMC currently employs over 20 staff, which include extensive expertise in education, management and biodiversity. So I'm just going to tell you a little bit about the Merri Creek. Some of it you will know, some might be new to you. So the Merri Creek catchment flows into the Yarra River, so it's part of the Yarra River catchment, and then into the Port Phillip Bay. You can see the map there on the left is showing the major sort of landscape context there, the main areas that, main uses, I suppose. So the dominant land uses currently are industrial, which is sort of more in the mid-catchment, agricultural, is much more in the upper catchment, but it's definitely changing quite rapidly to be a much more newly developed suburbs in the upper catchment. So newly developed suburbs such as Craigieburn, Donnybrook, Wallen and Kalkallo. So the land use is changing quite rapidly. And then of course in the lower reaches we've got highly urbanised suburbs that have been around for quite a while, including Coburg, Northcote and Brunswick. So even though there's been rapid change to the catchment, the Merri Creek and surrounds host many threatened ecosystems, including the plains grasslands, shrublands, swampy woodlands and other forests. There's also an amazing observations of growling grass frog, our threatened growling grass frog, the golden sun moth, murnong or the yam daisy and an occasional platypus. Protection of riparian zones and surrounding landscapes are guided by several strategies and legislative instruments. So that includes Melbourne Waterways Healthy Waterways Strategy, the EPBC Act, the Flora and Fauna Guarantee Act, the State of Environmental Protection Policy or SEP, Merri Creek and Environ Strategy 2009 to 2014. If you'd like to know more a bit about the Merri Creek geology and geography, we actually now have a virtual tour available on our website. So I can put the link in the chat towards the end of the presentation, but you can also just go to our website at mcmc.org.au. So some of the historical catchment issues. Merri Creek was traditionally known as the wasteland, mainly because it was used as a rubbish tip. So it was mainly waste disposal. There were a lot more abattoirs, tanneries and manure deposits along the creek, as well as construction sites. It was considered dumping areas for construction sites as well. So you can see that image there that was taken in Brunswick East in 1986. And also continually there has been removal of Indigenous vegetation. However, the local community took a stand and said enough, and the formation of the Friends of Merri Creek in the late 1970s occurred, which has culminated in over 45 years of revegetation efforts. The establishment of MCMC occurred in 1989, and since then there's been very strong partnerships with member councils, EPA, Melbourne Water and others. Despite all this amazing work, however, Merri Creek was named Melbourne's most polluted waterway, well, that's what The Age said, in 2011. So the final slide that I wanted to present was on the current water quality issues on the Merri Creek, particularly surface water and the benthic accumulation. So what's accumulating in the soil on the bed layer of the creek, which is equally an important issue as well as the actual surface water. So stormwater runoff, of course, is a really big issue, and most of us are quite familiar with that. Not just the contaminants in it, things like litter and oils and petrols and detergents and things from our streets and residential and industrial areas, but also the flow regime, which Edmund will talk about a little bit later. But one of the issues is that what we're having, and this is connected with climate change, is that we're having much more frequent rain all at once and then nothing for quite a while, and of course it's constantly changing. So for some species like platypus, who we'd love to see inhabit more areas on the Merri Creek, unless that flow regime changes, it's quite impossible. So platypus actually need quite a bit of a good flow all times of the year, so they don't really respond well to low periods for quite a while and then suddenly lots and lots of rain. Obviously the other issue there is too, not just the amount of water coming in, but also the pollutants coming with it that a lot of the times kill their food source, water bugs for the platypus. Sediment and turbidity issues, with which Dr. Kath will be talking about quite a lot, but yes, we do get a lot of sediment coming into the Merri Creek. A lot of that has been from new housing developments further upstream, and in fact our manager at MCMC, Louisa McMillan, put together an investigative report on tracing some of that turbidity a couple of years ago, which you can see on the website. Also, we have industrial discharges, including toxicants, so things like organochlorides, PCPs, which are polychlorinated biphenyls, which were banned, but they are still appearing in our benthic layer and in our surface water at times. More recent contaminants include PFAs, which are perfluorinated compounds. So one example of where they're used in lots of different things, but one that's quite frequent on the Merri Creek is firefighting foam. So when there's been a fire locally and they use a foam to suppress it, which works much better than water in certain fires, if that foam ends up in our creeks, yes, these PFAs also end up in the creek as well. Litter, of course, the major issues that we have with litter are mainly plastics, particularly soft plastics, probably about 70% of what we pick up. There's a number of us that do community litter pickups, and we collect the data, and the data is showing predominantly it's still soft plastics, and most of what we're getting in litter, what it's made out of, is plastic, whether it's soft plastic or hard plastic. Rapid urbanisation, so a lot of those things I've just talked about there, particularly sediment and litter, are quite directly from rapid urbanisation if there's not a lot of controls or checks being done. Modifications and diversions of the creek, so bank erosion, particularly when there's lots of compaction, can cause in-soil movement, which then of course increases the turbidity. Climate change, as I mentioned briefly, particularly affecting flow regime, lack of flow or too much at certain times, and of course affecting the temperature as well, and loss of habitat and increase of weeds. So now I've depressed you all, I'm going to actually pass you over to Dr. Catherine Lee, who hopefully will actually cheer us up a little bit. But also the other thing I just wanted to mention there is that if you are interested in learning more about the history of restoring Merri Creek, there's a fantastic recorded webinar on our website with Anne and Bruce McGregor, who are the founders of the Friends of Merri Creek. But other than that, I think I'll let Catherine take over. Just before Catherine starts, I just want to give you a little bit more information about Dr. Catherine Lee, who's done some amazing work. She's a freshwater ecologist and lecturer at RMIT University with the School of Science, within the School of Science, and is an associate investigator with the Australian Research Council's Centre of Excellence for Mathematical and Statistical Frontiers, or as I can't say.
ASIMS.
ASIMS, thank you. I'm terrible with acronyms. Kath actually moved to Melbourne from Queensland at the beginning of 2020. Bit of a bad move, wasn't it? Just as we started lockdowns, and has been working with MCMC and councils to help them improve waterway health and monitoring. I was just going to mention quickly too about the Centre of Mathematical and Statistical Excellence. Several organisations have provided funding support for this project that Dr. Kath's just about to talk about, including the City of Whittlesea, City of Moreland, RMIT University and ASIMS. Sorry about that, everyone. RMIT is a global university of technology, design and enterprise, ranked third in the world for its environmental, social and economic impact. The School of Science within RMIT has a multidisciplinary focus, enabling our researchers and students to collaborate with experts across industry and the university. It brings together Australia's top applied mathematicians and statisticians working with partner organisations to engage in research programs that combine innovative methods for the analysis of data. We thank the cities of Moreland, Yarra and Whittlesea and Melbourne Water for funding this webinar today as well. Thanks, Kath.
Thanks very much, Julia, and hello to everyone. It's great to be here today. I'd also just quickly like to acknowledge Bio2 Lab that have worked together with us. They were instrumental in providing the sensors, the water quality probes, and in their installation and maintenance of those probes in the water quality monitoring sites that I'll tell you a little bit about soon. And for further information about this particular project, you can please feel welcome to contact me either via my email. I'm also on Twitter, and to acknowledge my collaborators on this work from RMIT, Dr. Savandi Kandanarachi, and also Mr. Bhargav Rial and Caleb Holden. So I think you've got a bit of an idea from Julia's introduction about why water quality matters, but I'll just provide a little bit more background for you. Stream water quality just changes constantly, and in terms of turbidity, which is the particular RMIT project we were focused on, a naturally high turbidity in rivers, it's a really major ecosystem and human health concern. And so that makes it a really important and commonly monitored water quality variable in river management. Now, if we think about Merri Creek, high turbidity that sometimes occurs in Merri Creek happens in part because of inputs of litter, so rubbish coming in from the catchment, sediment and other pollutants via runoff, stormwater drainage systems. And then, as Julia was pointing out, there's rapid urbanisation and other land use changes happening in the upper catchment. And then throw on top of that climate change. So urban creeks, with all this going on, and Merri Creek's no exception, they can often get highly turbid waters. Now that means it's a lot cloudier than usual, and you can see the difference in this little schematic here on the screen. We've got some turbid waterways on the left and a nice healthy system and waterway on the right. And I hope I've got my left and right correct there, because I often mix them up.
Doing well.
Thank you, Julia. So often we see these increases and peaks in turbidity come following some rapid, some rainfall and then runoff that's happening in the catchment. And if you've been down to the creek lately, you'll probably notice that because we've had the rain recently. The water levels are up and the water's quite cloudy compared to usual. So that probably also helps to answer the next question I've got on the screen there. Why monitor turbidity? Well, one of the reasons is because high turbidity can indicate the presence of excess suspended sediment, nutrients, particulate contaminants from the land in the water. And these can adversely affect water-dependent plants and animals living in the waterways, and it also affects ecosystem condition. And then added on to that, high turbidity can really complicate and increase the costs of water treatment processes. If we think back to plants and animals, so if we look at the schematic here again, and imagine, that suspended material in the water column creating the turbidity, it eventually can settle out down to the bottom. And this can smother the gills of fish, for example. It can smother their resources and food sources, so other macroinvertebrates. So this creates a lot of problems for the living plants and animals in the system. That's just one example of why we want to monitor turbidity, so that we know what's going on in the catchment, and if we can actually try and pinpoint where high turbidity and when high turbidity is occurring, and so we can then do some effective management. So although timely and accurate monitoring of turbidity is really important for delivering effective management, and many water management agencies are really interested in developing networks of sensors that can monitor turbidity throughout stream networks and raise awareness of water quality by distributing a whole bunch of sensors throughout their stream network. That's really cost prohibitive. So that's why we want to see if new technologies can assist us. And that's really sort of entering into why this project and what this project is about that I was involved in. So at the start of 2020, as Julia said, when the bushfires were happening, and then we had COVID and what seemed to be endless lockdowns, this really accelerated the need to revolutionise some water quality monitoring and enhance the community engagement because of that limited accessibility we had to the waterways. If you remember at the time, we couldn't even go down and visit them for our own sort of interest and well-being. But it also meant that monitoring the waterways using some traditional methods, for example, a lot of the times we need to go down to the creek and collect water samples and then take them back to the lab. Now, if we can use sensors, and we call them in situ, so in place sensors that can monitor turbidity at high frequency, that really helps us along. Okay, and just before we get a little bit more into the project and the results, I just wanted to show you these two images. And you might be familiar with, this is sort of what the creek is looking like a little bit at the moment on the right. These are photos I took of Galata Tambor, which was one of the sites that we set up the sensors in for the project. The photo on the left in March is when the creek's been flowing, there hasn't been a lot of rain, and then you compare it to the one in September. You can see that not only the water cloudiness has changed, but also the water level has risen. It's higher, and that's because of the rainfall and the runoff coming down into the creek. And that's important for us to know, because when we want to try and monitor turbidity or look at models to predict turbidity from other variables that we might have data on, we can use things like rainfall and water level to help us predict what the turbidity might be. Okay, so for this project, we used a couple of new water quality sensors. So what were they and why did we use them? So the two different types we had, and again, we're interested in turbidity, was these little, and I've got an example here. You can see how small they are. They're called hobo pendants, and these measure temperature and light, and they work underwater as well. So they can measure and monitor water temperature and light, and they can do that at really high frequency. So you can program them, for example, to monitor every couple of minutes. We did it for every 15 minutes. And then we've got a turbidity probe. Now, this isn't the actual one. This is just an image of a turbidity probe that I pulled off the web, but it's similar to the one that we would have been using. And these can be telemetered as well. So if you see here on the right, you can see the little telemetry station that's solar powered that connects to this turbidity probe that's in the in the creek here. You can see the cord going down to it. This is at North Fitzroy, and here's the Galata Tambor site and the little sensors that we used. One of the other benefits of using these, so with the telemetered system, that can provide data so that we can then view it in real time, and this was monitoring every 2 minutes. And the little hobo sensors, they are Bluetooth connect enabled. So there's apps that you can then connect to the sensor and read out and look at the data in real time.
Kath, just on that, the app, I think you have to be close to out in the field, don't you?
Yeah, you do. And that was something I was going to mention towards the end, just, because I didn't want to sort of like get everybody down again at the beginning. But yes, it has Bluetooth, we all know, has a limited, distance that you can connect. And that means that there's potentially some issues as well once you put it in water. But I'll get to the punchline on that a bit later on. So one of the issues around this, as I was mentioning, collecting data can be quite expensive. So, and although putting these turbidity probes in may mean that we don't have to actually go out to the site and collect a water sample to take back to the lab, these probes and that whole system can be quite cost prohibitive for agencies, particularly if you want to put them everywhere. So we were interested to see whether we could use these little sensors that are much, much cheaper to see if we could collect that data and if it related somehow to turbidity, so that we could maybe put them in lots of different places and get a better understanding of turbidity across the creek, but not costing us, an arm and a leg. The reason why we thought they might be useful to indicate what the turbidity is because water particles that create that turbidity and the cloudiness in the water, they actually absorb more heat than the surrounding water molecules. And so we thought there might be a relationship there between underwater temperature and turbidity. Now, they also absorb more heat, the particles in the water, when it's sunnier and during the day, so during daylight hours. So that also meant that perhaps underwater light might also be useful. And at the same time, we were thinking that, well, light penetrating into a water column doesn't go down as far when the waters are turbid. So that there might also be a more direct relationship between light and turbidity there as well. Of course, light going down into a stream is going to be affected by things like the time of day, the time of year, how much cloud cover there is, if there's overhanging vegetation or other structures that shade the stream. So it's not a straightforward story. But anyway, we crossed our fingers and we wanted to explore this. And you can just see, I've just got this photo up here so you can see in terms of, how spatial, where the sensors were. So Galata Tambor both had the turbidity probe and 2 hobo sensors, and the same at North Fitzroy. And you can see us here having a good time installing those in the creek.
Well, we were pretty excited, weren't we? Because it was sort of just in between lockdowns. So none of us had been out much. So we were pretty excited. We were. I can see that there's a comment in the chat. I'm just wondering if there's any questions so far, Julia. No, I've just added some information that people can look on our website about that I briefly mentioned. But yes, it's a good time to mention to everyone that if you do have any questions, feel free to add them in the chat, and I can ask Catherine for you.
Brilliant. Okay, so now we're going to have a look at some data now, and this is where we've got all excited, and now we can, have a sit back and think, oh, okay, there's some issues here. We encountered some technical glitches. Now, in a way, I wasn't surprised by this because, as Julia mentioned, I'm involved in some other projects that are looking at trying to resolve some of these issues. When we collect data through sensors, these are technological equipment, electrical equipment, they're going to encounter some faults. So I'm involved in another project that's developing methods to try and automate the system of identifying when we've got a fault in the data and hopefully correcting that. Because once we're getting in this big data from these sensors, we can't just do that manually by sight anymore when we get the data. It's just going to take too long. So it sort of defeats the purpose. But I thought there'd be some technical glitches, but I didn't think there'd be as many as we came up with. So you can see this is the data for the turbidity probe from Galata Tambor at the top and from North Fitzroy down the bottom. It's the blue line going along December 2020 through to September 2021. And at least at first, it looks like it's ticking along quite as you'd expect, going up and down a little bit, not moving too much because there hadn't been a lot of rainfall. We got a bit of rainfall in March and you can see the turbidity goes up. So that's as we'd expect. But then it starts doing some really weird things. It's just going rapidly up and down, just too much that would actually be real. So that triggered us to think, oh, there might be something wrong. And so with the help of Bio2 Lab, we had to actually remove those sensors and do some work on them and maintenance. So that's why we've got these big red squares where there's just missing data. And the reason why there's a line on the North Fitzroy one was just because this is the last data point collected and this is the next one, and it's just done a line of best fit. So there's not actually any data there. And the grey boxes are where I've just pointed out examples of what I call bad data, where it's just doing really weird things. It's just dumping up and down just too much, or it's flattening out to zero, and we just wouldn't expect to see zero turbidity, so absolutely clear, crystal clear water in the creek. So we know something's wrong there. Now, the other problem with this was that these little hobo sensors that we were hoping that could help us predict or understand turbidity, we had used the equipment where the turbidity probe was installed to sort of anchor these in the creek. So whenever the turbidity probes had to come out, these had to come out as well. So we also didn't have the data for these during those missing periods. Now, it turns out these turbidity probes were faulty. It was a manufacturing fault. So it wasn't anything that we were doing, and it was just sort of disappointing, but it couldn't be helped. However, don't get too upset yet, because there is some good news. Because, as I said, we were suspecting that this might be happening, we were looking for other ways that we could get data and have a think about how these different water quality variables might help us understand and predict turbidity. So we looked for publicly available data that was of good known quality, and we were able to find some for turbidity and water level at Merri Creek that was collected and available through DELP. And you can see the time series here of that, the turbidity in the brown. And this was from January 2013 to February 2014. And in the green, the water level. Then we were also able to get rainfall at a weather station a bit further upstream at Somerton. And you can see a nice relationship, which is what we were sort of talking about earlier. So this is good that you can actually see that in terms of the data. The blue line is the rainfall, and it's sort of like there's a bit here and there. And then hopefully you can see it. There's a big peak in the blue line around May 2013. And that correlates just after that, pretty much right on top of it, you're seeing a spike in turbidity and also the spike in water level. So those relationships we were talking about earlier that you can see in the data. Then we were also able from the Bureau of Meteorology to get air temperature, maximum air temperature, and what's called total global solar exposure data. That's sort of a type of solar irradiation data. And you can see in the red and the yellow here, you can really see that seasonal change and trend and pattern. So you're getting lower temperatures as you'd expect and less global solar exposure at Melbourne Airport, which is where the data was from, during winter than you do in summer. And there's also variation around that sort of day to day. So this was daily data, known quality, and we were thinking that the total global solar exposure data might give us some insight as to, how it might relate to the light we were trying to measure. And also the air temperature might give us some relationship or understanding about the water temperature we were measuring, because there's a really close relationship between air temperature and water temperature within reason.
Kath, we've actually got a question,
Right.
which is great. Really interesting question. Has there been any small-scale proof of concept studies to see how automated and person-collected data align up?
Yeah, we've looked at that. I can speak to one example I know. So before I came down to Melbourne, I was working at Queensland University of Technology in Queensland. I'm a Queenslander, everybody, sorry.
We love you anyway.
So we were looking at trying to develop these models to automate the process of anomaly detection or working out when a water quality probe was giving us faulty data. And part of that, in developing all those models, we had to also try and see if we could predict, for example, nutrient or sediment data from the sensor data in the first place to see if it was, worthwhile doing this. And so as part of that project, we were looking at the lab data and the sensor data, and so that we could compare them and see how well they correlated. And, when it's working well, when the sensors are working well and they're calibrated regularly, they're maintained regularly, it's very good. So generally we expect it to be good. But the sensors need, attention and care. Just like we would have water quality assurance and control processes when we're in the lab.
Yeah, absolutely. And I think that's something I know my Water Watch volunteers and I have about 8 groups that monitor on the Merri and Darebin Creek, would be quite interested at their regular site if there was sensors put in there, because they'd be a really good check as well. So that is definitely something that we're, call to anyone doing further research like this, let us know. We've got another question as well, Kath, if that's okay. Do we know what devices DELP were using in 2013-14, and if they are still monitoring at waterway sites, and which devices, apps they are now using?
Yes. So I wouldn't be able to tell you off the top of my head what the particular pieces of equipment were that collected these data right now. But yes, they are still collecting data for, we had to restrict ourselves to 2013 to 14 in order to make sure that we could get data across all these variables for the same period of time. But if you do go to the DELP site, you can actually find, they have their water quality portal. I think it's called WIMP, something like that. But it's WMIP. I think it's Water Monitoring Information Portal. And you can find where the different sites are around the Melbourne region, and I think even maybe outside of the Melbourne region, because it's Victoria as well. So there's data out there for sure, and maybe we can put some links to that.
I was just going to suggest that, Kath, when you're finished, if you think of it, and you can add that one to the WIMP. That would be great.
And that's also available. I think you can get to some of that data via Melbourne Water as well.
Yeah, Melbourne Water's got an excellent website of lots of data as well. So I will actually try and find that. And if I don't in this presentation, I will email it out to everyone. They've got some amazing data available as well, from not just water quality, but habitat restoration and a whole lot of other stuff. So yeah, there's lots available online.
Great. All right. I've got a couple of more slides to go. And here's where we get some exciting results. So it turned out that using that data that we got from the 2013 to 14 period, we could actually predict turbidity really well. And I'll just quickly go back to this other slide. So we were using rainfall, water level, temperature and solar exposure to see if we could predict turbidity. And we knew what turbidity was because we had the data for it. So we looked at how closely our predictions were to the actual data. And if you keep this brown time series in mind and what it looks like, now on this slide, you can see it repeated here in these three plots in the black line. So we used a few different modelling techniques, different models to see, based on sort of the literature and what we knew in terms of modelling, which types of models might work well. We use them to try and predict the turbidity, and you can see we're predicting it one day ahead from about August 2013, and we use this initial part of the time series to build our models, and then we're testing them here. And the blue line is actually what we were able to predict. And if you squint, you can see there's a blue line and a black line. So you can see when you can't see the black line very well, it's because we've predicted the turbidity so well that the lines are basically on top of each other. So you can see that the three models did really well, but if we look at this last one, it's a little bit more off. So it's not as good. So we had two really, really good models here, what I've called ARIMA and GAM. Happy to talk about that with other people or at the end if people are interested, but you don't really need to know that. The grey shading is our sort of confidence in our predictions. So we know that the true value sort of will fit somewhere in that grey shading. So although this was the best model, we're less certain about the prediction than we are for this second model. And the reason I point that out is because this first one, which had the blue line is really, really close, it only wanted to use rainfall and water level to predict turbidity. But this almost best model, which is sometimes a little bit out, but we're much more confident in what we're predicting, it needed also, in order to get that increased confidence and accuracy, it needed to include the air temperature and the solar exposure data. And so we got really excited about that because it means that perhaps there is potential for underwater light and underwater temperature to help us when we're trying to predict turbidity, as long as we've also got some other really more closely aligned variables like rainfall and water level, for example. So where to next? Well,
just a really quick question for you too, Kath.
Yeah, I'll go back to that one.
Yeah, so someone just wanted a bit more clarity about what is the difference between the second and third models there, between GAM and LSTM.
Yeah. So can you see my mouse if I move it around?
Yes.
Yeah. Okay.
I can see
so
it. Yep.
You can see that with this LSTM, which stands for long short-term memory model, and the GAM is a generalized additive model. With the LSTM, the blue and the black lines, they look good in terms of the values, but it's offset, like it's not predicting it when it's actually happening. And we really want to know when turbidity is going up or when it's going down. We don't want to be sort of too late off the mark for that, and or having the wrong value. So the lines are much closer to each other in the second best model. So that's sort of the main difference. If you're wondering why there aren't grey shading around here, it's not because we're really, really confident. It's because that third best model is a much newer type of model that people are developing, and the way to work out your confidence around it is really, really complicated, and the coding to do that hasn't yet been written.
Oh, maybe Edmund can write that. He's pretty good at coding.
Yeah, so I should have pointed that out because, if you're looking at the shading, you might go, oh, yeah, but that's really good. But it's just because we don't know what it is.
And I'm sorry to rush you, Kath, but you've got a couple of minutes left.
Yeah, that's perfect, actually, because what I wanted to say was we really need to keep going with this because we've got sort of some indications that it might be useful, but we don't have the data yet for the proof of concept because we had those problems. We've sort of got some indications that it might be useful. The other thing, we really want to, part of this project was facilitating making water quality data accessible to the community. And as Julia hinted at earlier, we had problems. So when I was testing these at home in tap water, the Bluetooth was fine. As soon as we put them in the creek, we couldn't get the connection anymore. So I suspect turbidity had a lot to do with that. So turbidity is a problem in more than one way. So we're still sort of looking at how to make the data more accessible. But again, good news, and just quickly, we now have a new turbidity probe that Bio2 Lab has installed in a new site on Merri Creek. It's in Somerton. It's a bit further upstream from Galata Tambor. And this is some data that it collected just in the last week. The blue line is turbidity, and then it's also got water level and rainfall from Somerton bomb site. And if I can just move that out, there we go.
And this is accessible for everybody, isn't it?
Yeah, that's accessible to everybody. So I've got the link there. It'll be available. We can make that available to everybody. So that's really exciting. And we've also got a fact sheet that you can on the project that you can access. So thank you.
Oh, that's wonderful, Kath. Thank you so much. And yes, I'm pretty sure that probe that's on there now at Somerton is funded by the City of Whittlesea. Is that correct?
Yes, that's right. Yeah, so thank you to the City of Whittlesea for that. And it's continuing to be monitoring data because it's sort of like a replacement for the 12 months of monitoring data that the City of Whittlesea funded, but we couldn't do because of those manufacturing faults in the original turbidity probe.
Yeah, so it's fantastic that all the lessons we've learned, we're able to, it's great that there's some projects still happening to continue collecting that data. That's fantastic. Thank you so much, Kath. I'm actually going to introduce Edmund and run his PowerPoint presentation. So we're just talking about the City of Whittlesea, so it'll be really great to hear some of the solutions and recommendations that both the City of Whittlesea and the City of Moreland have been putting into practice to reduce these issues with turbidity and our other water quality issues. So Edmund Lascaris is the Stormwater Management Specialist at the City of Whittlesea. Edmund also teaches the Smart Cities Internet of Things course at the Whittlesea Tech School in Epping. He's got a really enthusiastic bunch of students there. The focus of the course is to teach students how to build and program water quality sensors to support improvements to waterway health. Students have already deployed 6 water quality sensors and are currently busy developing technology to support other environmental sustainability projects. So we look forward to hearing from you, Edmund. That's fantastic. I'm just going to share my screen with your presentation.
Thanks, Julia. And it's good we've had the background from Kathy as well on turbidity, so it saves a bit of time from me. I'm only going to speak for 10 minutes. So I acknowledge we're also talking about the Merri Creek, but today I'm going to sort of jump between Merri Creek and Plenty River because both of them are in the City of Whittlesea. And we were very lucky. You can see the Aniene Reservoir, and below that the sort of snake-like figure of the Plenty River. Melbourne Water have been doing a lot of work in the Plenty River and the Plenty Gorge, looking for platypus, looking for the food sources which they eat, and also looking at the vegetation which is needed around the waterway to support the platypus. We're very lucky. We have platypus in the Plenty River, and we want to safeguard them. But as I'll show you in just a few slides, they're under threat. In fact, they'll probably disappear from that catchment within the next 30 years. So next slide, please, Julia. And of course, we use, in the previous study, they used a technique called eDNA, which is take water samples, a bit like a PCR test for COVID, to test to see if the platypus are there, not that the platypus have COVID. And we try to verify those findings with real sightings of platypus. This one was just taken recently in South Morang on the 26th of July. So it definitely proves we have platypus there. Next slide, Julia. Now, with the Melbourne Water Work, they found there were 5 conditions which were affecting the viability of platypus in the Plenty River. The first one was high flow events, which typically happens when the water levels rise significantly. That happens when we have rains, and that's because we've built so many houses and roads that now every time it rains, it just rushes into the Plenty River. The second parameter is we call cease to flow events. That basically means the river stops flowing, and that can happen during the peak of summer and also during periods of drought. The third one is litter and entanglement, particularly challenging for the platypus because we've had platypus deaths because they get stuck in hair ties, rubber bands, etc. And that's mainly because litter, which is on the road, goes pretty much directly to the Plenty River. It's very difficult to stop. Turbidity we've had a great discussion around turbidity. That's a big problem for the Plenty River. And the last one is what we call riparian vegetation. That's all plantings all around the waterway, both in and around it. We desperately need more vegetation around the Plenty River. Next slide, please, Julia. So this is a photo of the Merri Creek, and you can sort of see the turbidity issues which the Merri Creek, and that's been spoken about during this presentation, but we have the same issues with the Plenty River. Typically, it's a result of urban development. We have disturbances in the land, and when the rain events come, it just washes all that mud and silt into the water. Next slide. So with luckily with Kath and with Bio2Lab and other agencies, we've been lucky to explore a whole range of sensors which to see which ones are most beneficial for protecting our waterways. The water level sensors are quite easy to install and very robust in the field, so we're going to continue work with them. Turbidity sensors, because of the nature of the data, we really want to continue working with them. They're expensive, and Kath has been telling us, or explaining how there's other lower cost turbidity sensors. So we're exploring both of them, and this research is very important. Temperature in waterways is important too. During summer, if you have a rain event, that can discharge a lot of hot water into waterways, which is not good for the animals there. And also, if you don't have enough vegetation around the waterways, there's not enough shade to keep the water cool. And we did have a large fish kill event earlier this year, and that was because of low oxygen levels in the water. So dissolved oxygen probes can also be used. But typically, we'll just focus on the water level sensors and turbidity sensors. Next slide, please, Julia. And we're hoping to install over the next few years an array of sensors, both in the Plenty River and also tributaries feeding into the Plenty River. And that's because it's important to sort of see which of these small subcatchments may be contributing to what we call pollution events. And that allows council officers and other agencies to go and investigate why the water quality is so bad in some of those areas. Next slide. As Julia mentioned, I really like working with the community. Since 2013, we've been developing technologies and also sensors which we can use. It really motivates young people to be able to work on environmental projects, which are especially local, and including if they use technology. So these particular students, and even though boys are represented here, I also teach girls as well, but unfortunately this shot is only of the boys. They submitted this particular project to the Young ICT Explorers competition and finished second in Victoria for their age group. And they were specifically using temperature, pH, and conductivity sensors to monitor a waterway. Next slide. And their work culminated in the launch of our first sensor, also with help from researchers and agencies such as Bio2Lab. This one's solar powered, and we placed it in Mill Park, downstream of an industrial catchment, which was known for notorious for pollution events. And we also installed a sign, which you can see here on the right, which has LEDs, which was giving the locals a bit of a representation on how clean this particular catchment was. So it had 4 different levels of pollution, if you like, or good to bad. Next slide, please, Julia. So the culmination of this work has now been a year-long course, which we deliver through the Whittlesea Tech School based in Epping. We use little computers, but it's mainly just sort of teach secondary school students how to build these sensors, how to code them, and then how to get the data from them to interpret. You can see the great work that Kathy is doing through the university and also with her students. Part of this work sort of underpins that. It's providing the skill set for the next generation of students coming up who will have an interest in this particular subject area. And next slide. And this is a very quick example of one of the sensors which was deployed more recently. We use sensors for a whole range of things. This one measures water level, and we had to test a particular water body to see if it was leaking or not. and also if it was getting enough water to support the biota there. So we can use these sensors to solve small problems and also big problems. But for the students, we were just focusing on this one particular small catchment, just as a proof of concept. Next slide. I'm racing through, but it's good. This is another dashboard provided by Bio2Lab and sensors for Bio2Lab. We have a small frog, a quarry, which has got growling grass frogs. Every October, we have to pump water from the Merri Creek into that quarry to support the breeding season for the growling grass frogs. And as you saw from the Merri Creek, we're very interested to understand if the water quality in the Merri Creek is suitable for pumping in, because obviously if it's very turbid, we shouldn't be pumping it into this particular precious catchment. So it just goes to show how important some of this data is for protecting the local biota. Next slide. Obviously, some of our slides are very technical in terms of the data which is presented. This is a really good dashboard which is community focused. This one is from the documentary movie 2040, and it shows a town in America where they're monitoring the water quality. And you can see on the right, the creek is called Plum Creek, but they're measuring things like water level and level of dissolved oxygen, the turbidity, and also the creek temperature. So these are really, really simple parameters, important for us, but also important for the community. And we would simply replace the fish on the left-hand side with a platypus, a happy or sad platypus, depending on how the water quality was. Next slide, please. I'll be very quick. We've talked about some of the problems, but the solutions are very important as well. We really need to look at a new technology, which is called the smart tank. And basically what it does is it's able to predict rain events and get rid of some of the water in the tank before the rain event, so it acts like a sponge. Next slide, please, Julia. And this is a smart tank which we have installed at Mill Park Library. So it's working currently, and we hope to install some more. And next slide. And we can just jump to the next slide because I'm just conscious of time, but that's
Is that on Monbolt Creek, by the way?
That is Monbolt Creek.
Yes.
So the link, you can just do a quick search for that. It's a fantastic project using smart tanks to protect platypus. Next slide, thanks, Julia. And we hope to do something very similar, sort of a smaller version of it, perhaps with 100 or 200 houses. And we would simply recruit people within the Plenty River catchment who already have existing rainwater tanks and be able to instruct them using SMS text messages as to when to release water from the tank and how to release it. So we're going to probably explore that model in the near future, and I'll welcome any questions in the future. And after this presentation, talk about it a little bit more. Next slide, Julia. There's a lot to cover, unfortunately. We can just, community planting is really important around waterways. So that's very important to engage the community. And in terms of a sensor application for that, we can see it on the next slide. We use young people, students, and the community to help us. As we do the planting, we record the GPS location for the plant, the species, and also the time of planting. And the hope is that as we revisit these sites every year into the future, it will be a great portfolio of data for the people to understand how well this community planting project is going along the creek line. And a few more slides, we're almost there. This one is really cool too, because I teach students using a little computer called the Raspberry Pi, and that little computer is only about $65. They have this new program which you can run on it called BirdNet Pi. You attach a microphone to the little computer, and it listens to the environment. As soon as it hears a bird call, it records it. It sends it to the cloud, goes to the Cornell University library, and tries to find a match. And you can see in the next slide that as I've had this Raspberry Pi, BirdNet Pi running at my house, it's easily been able to pick up 24/7. It gives you when it records the bird, what species of bird it is, how many times it's recorded it. And it's very important for us to monitor things like noisy miners, which you're probably aware of. They're probably too popular in the urban environment, and we're trying to create vegetation which favors some of the small woodland birds. So that's the end of my presentation. one more
Oh,
slide, just as a coverall. Thank you.
Oh, that was fantastic, Edmund. And I know it was a big ask to get all of that in 10 minutes. So that was absolutely fantastic and very exciting to see all the amazing work that you're doing with programming and things. So just a couple of questions. I'll just go through them quickly because we have got Arizo to her presentation. Yes, there will be a way of accessing this talk later on. It will be videoed and I will be sending you all a link to our website with it. And thanks, Kath, for putting a link to the turbidity data as well. So I think that's about all. Yes, that's great. So I think we'll let Arizo do her talk. I'll introduce Arizo while she pops her presentation up. So Arizo Hushmund is the Integrated Water Management Lead at Moreland City Council. She is responsible for implementation of Moreland's Integrated Water Management Strategy 2040. She's in charge of delivery of place-based integrated water management across Moreland, as well as providing advice on green infrastructures to other teams across council and private developers. Arizo is advocating for implementation of blue-green infrastructures across Moreland. Thanks, Arizo.
Hi, everyone. Thanks, Julia and Edmond and Kat. It was interesting to listen to your presentations. So I just go through a little bit of works that Moreland is doing to improve the health of our creeks, and obviously dealing with the growing list of challenges like climate change and urbanization and all the turbidity that Kat was talking about. So what we are trying to do in Moreland is recently in August 2020, we set a strategic direction and implementation approach for improving water cycle management. So we are trying to create a water sensitive city. A water sensitive city is a city that's livable, resilient, sustainable, and productive. So we have got a set of so we have got all these challenges that we need to deal with, and obviously with urbanization, we have got high amount of impervious area and pollution entering to our waterways. And one of the solutions is adopting distributed solutions across the catchment to treat water and slow it down before reaching to our creeks, to basically through biological and physical treatment. And that's could be through implementation of water sensitive urban design elements like rain gardens and wetlands and harvesting systems, rainwater tanks across the catchment in like a smaller scale or larger scale assets. So here it's a high level, so it's basically showing Moreland City Council that sits in two catchments. We have got Merri Creek, that the catchment drains to the Merri Creek catchment, and Money Ponds that drains to Money Ponds Creek. So in Merri Creek catchment, we have got few wetlands. We have got Myriad Guards wetlands and Jones Park wetlands, and we have got 3 different stormwater harvesting systems that basically they have got rain gardens. They treat the water, slow it down, and reutilize the stormwater for irrigation of a sports field, and then the remaining water, the remaining treated water will be go back to our creek, and that helps with slowing down the runoff and hopefully reducing the turbidity into our creeks and improving the health of our creeks. We have also distributed GPTs across the catchments, and that the gross pollutant traps, they trap the larger sediments and litters before entering to our creeks. And these are some of the photos of the larger scale assets that we have got, like the Jones Park wetland and the City Oval harvesting systems and rainwater tank, and the Merri Edgar wetland. We also use every opportunity to add more of blue and green infrastructure across Moreland. For example, when we are reconstructing a road, we are looking for opportunities to add a rain garden or a tree pit, and we are looking into broader benefits in terms of flood mitigation and reducing urban heat island effect as well. So as such, we implementing lots of smaller scale assets across moorland. We have got around 300 individual assets across moorland, and 177 of them are located in Merri Creek catchment. And our future project, which will be built in next few months, is the Mumba Park wetland that is close to Merri Creek in Mumba Park, and that would be hopefully a fantastic project for community. And we are placing a growling grass frog pond at the end of the wetland to basically take the treated water from the wetland into the frog pond for growling grass frogs. And that's end of my presentation. If you have any questions, happy to answer.
That is wonderful, Arazo. Again, did an amazing job in a very short space of time. And I don't know about you all, but it's very exciting to see some of these major projects coming in that are going to help so much with the treatment of our creek water. And it shows even more importantly that we do need to keep going with sensors, doesn't it, and monitoring to see, well, how effective are they? Because I think this is a problem for a lot of councils, is also having that funding to, yes, you put the infrastructure in, but what about maintenance and what about monitoring to see, well, how effective has it been? So it just really goes to show how even more important that monitoring is. That's fantastic. Not many questions in the chat. I think you're obviously all very comprehensive and everyone understands everything. So that's fantastic. So I want to just thank all our presenters today, Edmund, Kath and Arazo. They've done an amazing job in a very short period of time on some really complicated issues, really, that are very important for us all to understand more of. And I'm so glad so many of you were able to make it today to hear more about these fantastic projects. It's always difficult to try and get these types of things happening. So I'm really glad that we were able to do this. So this is the culmination. Thanks, Edmund. This is the culmination, and Alex, of lots of work from Dr. Kath and her team, and myself, I suppose, working alongside Kath for quite a while, as well as City of Whittlesea and City of Yarra and City of Moreland as well. So it's been absolutely fantastic. Thank you for those. Everyone's saying thank you so much. And thank you so much, everybody. Enjoy the rest of your rainy Friday.